Hey everybody, welcome back. This is going to be our first 6.3 video. 6.3 is a beast. So we are actually going to start off with some review questions. I have the answers right here because I know that some of you might want to, just do them on your own, check that you can do them. Some of you might want to actually hear me explain them. So if you just want to check answers, go ahead and pause your video, take some time to do the review questions on your own. When you feel pretty good about it, you can skip ahead to when we get to the Bernoulli trials below. If you want to hang out and do them with me, here we go. Otherwise, you can just totally skip ahead. So, first one. Number one, want you to calculate the least squared regression line. Oops, I didn't have the answer to that up there. My bad. That's okay. But anyways, calculate the least squared regression line for the data below. We want to state the correlation and coefficient of determination. So we have some kind of XY value thing going on. We don't really know what this data is, but easiest ways that we're going to be able to do our least squared regression line and get our correlation and get our R squared all in one go is if we put these guys in two lists and calculate our least squared regression line in our calculator. So that's what we're going to do. So let me get my calculator out. Here we go. So lists are going to be in stat. You are going to go into enter. We've got nothing in there. I'm going to go ahead and put my X's in list 1. So 38, 56, 59, 64, and 74. Awesome. So I got all the X's in there. The Y's are going to be in list 2. So 41, 63, 70, 72, and 84. Great. Okay. So lists are done. If you haven't used a calculator in a while, we might want to go into that mode and just go all the way down. Make sure all your stats stuff is on. Oh man, look, mine is not, so I'm going to turn it on. There we go. Okay, so stat diagnostics is on. Stat wizard's on. I'm good to go. So I'm going to quit. Now I'm going to go back into that stat button and I'm going to go to calc. Okay, calc. And I prefer, we are very used to using number 8 on linear regression, that A plus BX form. If you use the AX plus B, it really doesn't matter. But you just need to make sure that your value for your slope is actually where your slope is. The value for your intercept is actually where your intercept goes. So I'm going to select number 8. I'm going to make sure that the X list matches the list that I did and the Y list matches the list that I did. And guess what? They do. So I'm just going to go ahead and go down. We're not graphing, so I don't really care about storing the regression equation today, but I'm going to calculate everything. So it looks like we got everything that we need. Our A, or our intercept, is going to be negative 3.65966. I don't really care. Slope is going to be 1.1. We could just do 1.20, 1.97. Yeah, 1.197. And then there's that R squared, 0.988. And then that R is 0.99. So whatever we're looking at has a super, super, super strong positive linear association. Looks like, a really solid amount of the data is accounted for in our equation. So I'm going to write my equation because I didn't do that earlier. Oops. Don't forget your hat on your Y, because remember, this is a prediction. So negative 3.660 plus 1.197x. Okay. If we had values, or for our variables, we'd say where X represents this, where Y hat represents this, but we don't have any values there. So all good. All right. Number 2, review. Assume a distribution is that n means normal. And remember, your first value represents your mean and the second value represents your standard deviation. We want to find the probability of getting a value greater than 450. So here's the deal. I am going to draw a very rough curve because, why not? So in my normal curve, right, my mean is 360. My standard deviations are 50. So the next value is 410. The next value after that is 460. Right? And if I kept going, I don't really need to, so I'm not going to. But we are looking, okay, how many values are above 450? 450 is going to be somewhere over here. And that is not a nice standard deviation. So we have some options here. We can calculate a z-score and use our table. Again, like I'm kind of going away from using the table, not because it's bad, but because we're going to be using our calculator a ton today. We're going to be using our calculator a ton moving forward. So I really want us to get used to finding that area under the curve using normal CDF. So that is what we're going to do. Okay, so when we do our normal CDF, I'm going to kind of write it out off to the side, off to the left side right here, just so you know before we go ahead and put that into our calculator. So it's going to be normal CDF. And our lower is going to be that 450 because that's where I'm starting. My upper, now you can still put 1,000 even though we are rolling with, you know, some bigger values. When your standard deviation is only 50, you're going to be fine. You're still not going to hit 1,000. So it's okay if 1,000 is your upper. Mean of 360 and standard deviation of 50. Okay, sorry, it kind of got a little squished right there. But you're going to put all that in your calculator. You're going to push enter, and that is where I am getting 0.036. Just a little refresh, right? In the calculator, normal CDF is in second vars. So second vars, normal CDF. And I'm going to put all my values in like I wrote it out. So 450 is that lower. The upper is still 1,000. My mean right now is 360. Oops. 360. There we go. And my standard deviation is 50. There we go. 0.0359. Okay. And our last review one. So last review one, we are still using the same information from problem 2, but we want to know what value would have 80% of the data lie above it. So if I if I still have this curve right here, right? I want 80% of the data above it. I don't really know like where exactly that is, but honestly, it's probably somewhere over here. Just because I kind of know what it is. I mean, I can see the answer, but you know, if you think about it, 68% of your data is one standard deviation away, but we know that like there's still, you know, when you're 2 standard deviations away, it's 95. When you're 3, it's 99.7. That's coming from the middle. And so we when we still include those upper values, we know we're probably going to be less than 1 standard deviation below the mean there. So I am somewhere over here. We don't know where. That's kind of our goal, to find it. So we're kind of doing the opposite of what we just did in this last one. We need a place. We don't need like a percent. So we're not going to use normal CDF. We're going to use that inverse norm function. Okay. Couple ways you could think about this. Some of you guys have, you know, nice calculators where you can do like the left side, the right side, all that, and you don't really have to worry about thinking about how your curve is set up. My calculator, I always have to pretend that the left side is the side we're focusing on. So if I know that there's 80% here, I know that that means there is 20% left right there. So when I go to do inverse norm, that is going to be my area. The area is going to be that 0.2 because I know that my calculator won't do that, you know, that other side. So I'm going to do area is 0.2. The mean is still the same, 360. And the standard deviation is still 50. And I can do all this in my calculator, which is really great. Of course, you know, you could still find a z-score if you wanted to. You would just look at the 20th percentile on your table and then roll from there. So go back into second vars. Oops, my bad. Second vars, there it is. And inverse norm is number 3. Okay, area is 0.2. Mean 360, standard deviation 50. Oh, this calculator is very nice. Just kidding. The one I use in the classroom is not as nice, but that's a very nice surprise. So if I wanted to, I could put 0.8 and then I could go over to right, but I'm just going to stick with the left because I already explained that. But again, like if you wanted to go to the right side, you would still get the same answer. You would just use 80% instead of 20% like I did. So 317.91 or 92 is going to be our answer for that last one. Awesome. So it was a solid 10 minutes of review. We are now going to move on to some new stuff. So this is where it gets kind of this is where we get into some of the really crazy like probability stuff. Bernoulli trials. So every single trial can only have 2 outcomes, or our outcomes can be reduced to 2 outcomes. So when we think of these 2 outcomes, usually our 2 outcomes are classified as like one is going to be a success and one is going to be a fail. Now, success and fail does not have to be win-lose. It doesn't. Like sometimes it is. That's probably our most common success or fail. But sometimes like a success is just like hitting a certain value or ending a game or something like that. And I know that sometimes that can be reduced to like wins and losses, but really it's what you want versus what you don't want. Okay. Another name for these is, you might see it called like a binomial distribution. So I do want you to write, but I should have done that at the beginning. That's okay. So this is more of a binomial situation, right? And that binomial, like bi means 2, so those 2 outcomes. Okay. The outcome of each trial has to be independent. So that means like when I do one trial, like whatever happened in the first trial does not affect the second trial. So an example of this is like if I'm going to shoot a free throw and I know that we can argue, like what the crowd's doing or like how my, where my head's at or whatever, but shooting a free throw is an example of a binomial like situation where I have a success, I either make the free throw or I don't make the free throw, I have a fail. But every time I shoot a free throw, whatever happened the first time I shot a free throw does not impact me shooting a free throw again. And again, I know like, strategy wise, you could be like, well, I'm going to miss this second free throw on purpose because then I'm going to get the rebound and make 2 points and get more points. I get that. But just the act of shooting the free throw is going to be independent. Each one is not going to affect the other one. So just bear with me on that one. Okay. The probability of a success is going to be fixed for each trial, and that is going to be our P. So every time we're looking at our probabilities here, the probability is always going to be a success, always. Okay. The fail is just going to be 1 minus P. So I do want you to make a note of that. So failure probability is going to be 1 minus. Every time, because those are your only 2 options. Okay. Now, something that's kind of helpful for us to check is like, how do we know we're doing a binomial situation versus like a regular probability situation? So we have a really fun little acronym right here off to the side that I'm going to put called BINS. Okay, the B stands for binary. So there are, 2 outcomes, success versus fail. Okay, your trials, right? So every time you do this is going to be independent. Okay, the N stands for number because usually we want a certain number of successes. And this is usually going to be a situation where it's greater than 1 because we've done probability problems earlier in chapter 5 where we said, okay, what's the probability that I get at least 1 ATM working or something like that? So this is going to say like, what is the probability I get at least like 5 successes? And so that's a little bit different. So number of successes is usually greater than 1. You don't have to put the greater than 1 in there, but that number of successes is super important. Okay. And then our S is going to be success of P. So again, P, your probability is always going to represent success, and that's where that S is. Okay. So right below, it talks about a geometric setting. We're actually not going to look at that right now. I want to go and look at that later because sorry, a geometric setting is also a Bernoulli. I know I said binomial earlier, but we're going to look at a binomial, which is a type of Bernoulli trial. We're going to look at geometric setting in a different video. I don't want us to get mixed up with those. So you're going to go to the next page and look at where it says binomial setting. Okay. So a binomial setting identifies the probability of getting some number of successes, right? X successes in the n number of trials in a Bernoulli situation. So again, maybe I'm going to shoot 20 free throws. I want to know what is the probability that I get 13 or more makes in my 20, shots. That would be a binomial setting because I want a certain number of successes. I only have 2 outcomes, and I'm doing this trial many, many times. So we have a formula for a binomial distribution setting. It's right here. We're real happy about it, right? So this guy is on your formula sheet. That is going to be the most important thing that you need to know. So you do not have to memorize this. Yay. So that is a win. Okay, things that you do need to know is this. This is not on your formula sheet. So you need to understand how to, what goes in each place. So like you need to know that P stands for probability of a success. You need to know that 1 minus P is going to be your probability of a failure. And we kind of wrote that, on the front side as well. N is number of trials. So, in the example that I gave you with the free throws, I'm shooting 20 free throws. So that would be my number of trials because I'm going to go through it 20 times. X is the number of successes that you're looking for. Okay. So that would be if you, I wanted 13, right? I wanted to make 13. So X is like my number. Okay. Now, this part is really tricky. Because you remember in the past where we go, okay, I shoot 2 free throws. What are all my options? And it was pretty easy. We were like, okay, you could make and make. You could make and miss. You could miss and make. You could miss and miss. And we were able to do, all the possible combinations of shooting a free throw. It's really, really hard to do that with 20. I mean, we are going to be here for a very, very, very long time. So this right here, this N with the X, okay, the way you read it is it's read as like N choose X, or so number choose this many. So if you ever see that or hear me say, 20 choose 13, that means like this is the number of ways that I can get that. So you could totally find that by hand. You would do the number of trials you have as a factorial. Remember that factorial just means like if let's say my N is 20. Okay, it just means I'm going to be doing like 20 times 19 times 18 times blah, blah, blah until I get down to, 1. All over the number of successes you want. So let's say I wanted 13, right? I would do 13 times 14 times blah, 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 all the way down to, oh man, look at this. Okay, this would be the total possibilities of failures because you're taking the number of trials and subtracting the number of successes that you want. So this is the total ways to get failures. So super, super, super long problem. However, we can do all this in our calculator. I will show you where that is. So in your calculator, actually, I'll show you where it is later. Forget about it. But in your calculator, there is a way that you can get this, which is pretty much this at the same time, right? So we can use our calculator. Okay. And when you use your calculator, there is a place called math. So we would go to math, we'd go to probability, and we'd use a value that looks like this, NCR. Okay. That helps you do that, the number of ways to get your successes. And that's kind of like why I use that like Q the choose, because that C in there helps me remember like to use the one with the C. Because there's one with a P in there and we're not using that one. We are using this one with the C. So I have a number. I'm going to choose successes. Okay. Now, the mean of a binomial distribution is going to be your number of trials times the probability of getting a success there. And then your standard deviation is this formula right here. Guess what? These are on your formula sheet too. You just have to remember what N and P stand for. And we're going to be working with like N and P a lot, so I'm not really worried about us forgetting that. So these are on your formula sheet. We love hearing that. So that's really great too. Yay. Cool. So we're gonna look at this in example 1. We are going to do this the long way first, and then I'm gonna show you some shortcuts. It's gonna be very fun. Very, very, very fun. So number 1. So Quinn tosses 10 darts at a dartboard. Located at the center of the dartboard is his chapter 4 test. The probability that he hits the test is going to be 75%, and we want to know, or X is going to be the number of darts out of 10 that hit the test. So assume the dart throws are independent of each other. So this checks all of our boxes that this is a Bernoulli trials. Number 1, there are 2 outcomes. He either hits that test or he does not, right? That's really it. Even if he doesn't hit the dartboard at all, he is not hitting that test. Number 2, it says that the throws are independent. So great, we know that one throw does not affect another throw. We are doing this multiple times, right? We are going through 10 trials. We're probably going to find some probability on more than, one success. And we do have a success. A success probability is 75%. So we are good to go. So we want to know what our N and P, well, I just kind of did a little recap for us, but our N is going to be the 10 throws, and the P is going to be 0.75% for a hit. Because that's all we care about right now. That would be our success. All right. Part B says, what is the probability that, he hits the test exactly 5 times? So we are looking at probability that I hit the test exactly 5 times. Okay. So here's the deal. Like, I'm only looking at 5. So usually if I want more than 5, I'm going to have to go through my formula many, many, many times. So this is what I'm going to be using right now. Okay, I don't really have the ability to like show it, as I'm doing it. So hopefully you can see it on your notes. We can copy it down. So important things, right? Off to the side, we might want to remind ourselves that we're doing 10 trials. We want 5. So that's going to be our X. Okay. And then our probability still is 0.75 because that's a success. So I am looking on my notes at the formula. I'm going to fill in the pieces that I have. So we have 10 trials. We want 5 successes. The probability of getting that is 0.75 to the power of, we want 5 successes because that's our X. Okay. Times 1 minus 0.75 to the power of 10 minus 5. Okay, lots going on there. Lots going on. What we're going to do together is this new piece right here, this guy. Okay, so that 10 choose 5, I'm going to go ahead and put that in my calculator. And I know we haven't gone there yet, but that's okay. So we're going to go there together. So we are going to math. Okay, I'm going to arrow all the way over to probability right there. And number 3 right there gives me that NCR situation. Okay, we're going to push enter there. Now you're going to enter this as think of it as first number, second number. So my first number is my trials. So my number was 10. So 10 goes here, and then arrow over, we're going to have a 5 right there. Okay, so that means there are 252 ways to get 5, a success of 5. So that would take us a very long time to list out. So I'm really glad that we know how to do that now. So 252 ways to get exactly 5 hits if I'm going to throw the dart 10 times. Okay, so this is 252 right here. Awesome. Times 0.75 to the power of 5. Yeah, I could have done that. Whatever. 1 minus 0.75 is 0.25. And then 10 minus 5 is 5. Alrighty. So, rather than do, all the exponents and stuff for you, I mean, you can go ahead and pause your video. You can go ahead and trust that you can do order of operations. So make sure you do those exponents first. So these guys right here before you multiply by 252. But I'm just going to let you know that I went ahead and did it already. And I got 0.0584. So that's your probability of hitting the test exactly 5 times. So 0.0584 or 5.84% probability of hitting 5 times. Awesome. Cool. All right. Letter C. Letter C wants to know what is the probability that he hits it 8 or more times. So this gets a little bit trickier, right? My goal is getting a value 8 or more. Okay. So when you do 8 or more, you have to think about every single outcome that you want. So technically, I want probability of getting 8 plus, I also want probability of getting 9 times, and I want probability of getting 10 times. Oops. So I want everything. Okay, this is where it gets like crazy because I said we're going to do like some super crazy, super meaty probabilities. Here it is. So you are going to use what we did earlier up in part B. You're going to do that for 8, 9, and 10. Okay, your probability has not changed, but all of the values are going to be a little bit different. So let's look at our first situation, probability that we get 8. So that would be 10, choose 8, okay, times 0.75 to the power of getting a success. Well, I want 8 successes, so I'm going to raise it to a power of 8. Times 1 minus 0.75. Remember, that's your fails. You want 2 fails. So see how earlier we ended up with 5 and 5? Okay, now I'm making that connection and I'm going, okay, I want this many successes. I want this many fails. And that kind of helps me when we're doing these, super, super long ones. All right, I'm gonna get a different color for 9. So 9, I have 10 outcomes. I want 9 successes. 10, choose 9. Probability of getting a success is still 0.75. I want 9 successes, so I'm gonna raise it to a power of 9. And then same thing, 1 minus 0.75 to the power of, I'm going to have 1 fail if I have exactly 9. Okay. All right. And last one. Okay. Now I have 10 trials. I want 10 successes. This one's pretty easy because there's really only one way to do it. But we still have to do 0.75, right, to the power of 10 times 1 minus 0.75 to the power of 0. This one's kind of silly to set up, right? Because you know that there's only one way to do this. Wow, these 10s look bad. There we go. The marker's too fat. Anyways, there's only one way to do that, so that would be a 1. And then we also know that anything raised to the power of 0 is also 1. So again, this part is kind of silly, but this 0.75 to the power of 10 is still very important. So just for time's sake, because I am kind of keeping an eye on that video, and yes, I knew this was going to be a long one just with like the review and stuff. So if you've hung out for the whole time, fantastic. If you've kind of skipped ahead, it's all good. I'm just going to, for time's sake, I'm going to write down the probabilities that I get for each part, and you can go ahead and try to do those on your own still. But for this first part, for the getting exactly 8, I'm going to get 0.2816. Okay, for my second one for 9, I'm going to get 0.1877. And for my last one for 10 successes, I'm going to get 0.0563. And when you add all those guys together, you should get 0.5256. So pretty likely that you're going to get that. You're going to get, 8 or more. So 52.56% probability of getting 8 or more. Awesome. Okay, we got one more, and then we get to know how to do it the cool way in our calculator. And some of you guys are probably just like, I skipped ahead already. I'm not doing this. And this is totally fine. Okay, so what is the mean number of time he hits the test? And find the standard deviation for the situation. So way back at the top, we got these formulas. If we don't have these formulas, they are definitely on our formula sheet. So our mean or our expected value is always going to be the number of trials times the probability of getting a success. And honestly, all you got to do is fill in the blanks. So number of trials, I got 10. Probability of getting a success is still 0.75. So that's pretty straightforward. So I'm going to have 7.5. Now, does it make sense to hit the test 7.5 times? No, it does not. You can't hit the test a half of a time, but remember with like mean value and expected value, we just roll with it, even if it doesn't make sense for our situation. Okay. Standard deviation, same thing. We have that formula above, right? That's going to be our n times p times 1 minus p, all under a square root. So again, not awful. You have all those values. You just have to plug them in and then use your calculator. Okay, so standard deviation is going to be n is 10, p is 0.75. Oh, wait, we already found that. That's really nice. Okay, that's going to be 7.5, and then we could totally multiply that by 1 minus 0.75. So really, under your square root, you have, ooh, I didn't know that was space pen. That's a nice surprise. Sorry. Anyways, so this is really 7.5 times 0.25 in a square root. And then when you get that, that is going to be 1.3693. So how do we interpret this? We are going, on average, I made a little theta on accident. We would expect him to hit the test 7.5 times and vary from the mean by 1.3693. Yes, I know that does not make sense, but it is what it is. Okay, so the calculator is really awesome. I'm not gonna lie, but it also kind of sucks sometimes because it's a little tricky. Okay, so yes, our calculator will do the binomial distribution calculation for us. We love that. We don't want to go in and do, 10 choose 8, 10 choose 9, 10 choose 10, because some of these problems get really crazy, especially some of the ones that you're going to do on your homework. So binomial distribution is found under second distribution and binom PDF. However, be really careful here because this binom PDF one, this is when you use for finding an exact success. Okay, I'm going to show you. Okay, so that would be like if you're saying, I would like to get exactly this many successes. Ooh, that sounds kind of familiar. We definitely did that in part B. So we're going to use part B to kind of check our work. So ideally, we're going to use the same information, right? We are going to use this right here, this n equals 10, the x equals 5, and then the, oh my goodness. And then the p equals 0.75. We're going to use all that still when we fill that in for our, in our binom PDF. And hopefully we're going to get 0.0584. It's going to be really embarrassing, really awkward if we don't. But you know what? I'm not perfect. So yeah. Anyways, so when we use binom PDF, right here, it uses the form this. Okay. We're going to check our work from above. So if you need to make a note from part B, right? N equals 10, P equals 0.75, and X, my bad, x equals 5. Okay, we're going to plug that into our calculator. So everybody locate your calculators. This is super important. You want to know. Okay, so we are going in to second vars because this is a distribution. It's just a different distribution. It's not the binomial. It's going to be something a little different. Or sorry, it is the binomial. My bad, it's not normal. See, this video is too long for me. Okay, so we're going to go all the way down to binom PDF. That's going to be A, okay? And we're going to fill in our stuff. So our trials are 10, our p-value is 0.75, and our x value is 5 because we want 5 successes. Paste it. Oh, look at that. Perfect. That was going to be, I was a little nervous, but it's all good. That is what we got when we did it by hand. So I know that was a lot quicker, but it is important to know by hand because you might get a multiple choice at some point that has like you doing the binomial setup. So it is still really important to understand the formula and know how the formula works. Okay, so we just talked about how to do it with an exact amount. Now, how do we do it with something like part C, where we have something that, 8 or more times? I mean, you could go through and you could do PDF, PDF, PDF. You really could, and you could add all those probabilities. However, there is a function that lets us do it for a big range. But this is the tricky part. This is where I kind of get conflicted on, using the power of the calculator. So for an inequality, okay, you can use binom CDF, but the way binom CDF works always is it always calculates in your calculator x is less than or equal to your value, which is really tricky. Okay, so I'm saying it's really tricky because if you think about part C wanted you to get a value of 8 or more. When you do, if you want a greater than value, so for an x is greater than or equal to, oh my gosh, I'm sorry, it's always less than or equal to. Sorry. So for an x is greater than or equal to situation, you need to go 1 minus. Like whatever you don't want. The x is less than or equal to situation. And this gets tough because like usually you have to take out 1, and I'll show you what exactly that means, because guess what, we're going to double check our answer in part C. Okay, so part C, same exact thing, right? But we want greater than or equal to 8. So this is where we use CDF, and I don't actually know if this is why it's called CDF, but in my brain, like CDF, the C stands for continuous. So you can find all those values without doing them separately. And PDF is more like precise. And again, do not quote me on that. I don't know if that's what it's called, but that helps me remember it. And if somebody on YouTube's watching this and they hate it, I'm really sorry. But let's go ahead and go into our calculators and check this out. Again, remember I messed up. I think I said less than or equal to, but I put greater than or equal to. I don't know, but we're going to our calculators right now. Okay, so binom CDF is still in the second vars area. So second vars, go to binom CDF. There it is, part B. We love it. Okay, if I do, so I have to remember that my calculator will only do less than or equal to. So what I'm going to have to do is I'm going to have to do 1 minus at the end, even though I know that my goal is to get 8 or more times. So when I do my trials, it's still 10. When I do my probability, it's still 0.75. However, because your calculator will do less than or equal to, you are not going to put an 8 in there. Because when we subtract 1, we are also going to take away the probability of getting an 8, and we don't want to do that. So we have to do 1 less than that, because what we're going to do is we're finding right now we're going to find the probability of getting 7 or less, which is what we don't want. Once we find that probability, we can subtract it from 1. Okay, and 1 minus, My answer, boom. That is exactly what I got earlier. You could also write that as like 1 minus and then put your binom CDF stuff in there, but I kind of forgot to do that. So, but I'm letting you know that you can do that as well. Okay, listen, super long video. Super important stuff, really tough stuff. So if you have any questions, please do not hesitate to come in and get help because this is a really, really tough area. We're gonna do a different video on that geometric stuff. So thanks for watching and enjoy the rest of your day.